I will start with some kind of overview and general motivation for what's going to happen. So,
can you send us the slides afterward?
Definitely. So this part will contain some kind of physics maybe inside, but as you will see during the actual lectures, the physics will be kind of squashed, and most of it will be some rather elementary differential geometry. But still, what is this motivation? So let me maybe try to write it maybe in 2 columns. So one part would be like, so let's say, ordinary world. And let us start with data that one needs for 2-dimensional sigma models, meaning that like if you want to describe some strings moving in some manifold. So the thing that we should use probably, okay, there is a manifold M, then a Riemannian metric, and then either 2 form or maybe not better a closed 3 form. So this is and this is a Riemannian metric. And out of such a thing, we can write down now. Say if a map from a surface with a, let's say, conformal or pseudo-conformal structure going to M, so then we can write down the corresponding action functional, which is whatever it is, some integral over sigma of something. And then there is this kind of term corresponding to h, which one can write as integral of f star of h. And for that, we need to imagine, okay, it's an integral maybe over some y, and we need to imagine that sigma is the boundary of something 3-dimensional, and we extend our f also as a map going from y. A better way how to talk about it is maybe if instead of a closed 3 form, if we imagine that it is a what is called differential character, then we do not need to worry about this 3-dimensional y. And so what will be well defined is exponential of is. It will not use any y, but okay. And the thing is, as I said, this was something like happening in an ordinary world, and then there are some kind of generalized worlds. So, or maybe right here, Courant algebroids. So for one thing, already this triple, this data can be equally or equivalently phrased as a generalized metric in an exact Courant algebroid. Now, I will explain all those words later on, what they mean, which is maybe a bit funny to explain to many of you, but still, if you know those words, then pretend that you never heard them. Okay. And so what we're going to do here, we're just going to drop this word exact. So we're going to basically use arbitrary Courant algebroids. So imagine that now we talk about a generalized metric in an whatever arbitrary Courant algebroid. And so it's some kind of generalization of this data of G and H. And it turns out one can still define some sort of 2-dimensional sigma model. So this thing generalizes to some kind of, let's call it, exotic 2-dim sigma model. So what it really is some kind of boundary field theory, which is happening, a boundary field theory, which is happening on the boundary of some topological field theory, and the topological field theory is what is called the Courant sigma model. So on the boundary of a topological field theory, which is, and the topological field theory, the Courant sigma model. So maybe in some sense one can see already here some boundary thing happening. There is this sigma which is on boundary of y. Well, we actually don't want it, we want to get rid of that, that's why we want to have this differential character. But okay, might give some impression of what's going on. Okay, I will tell you later what those things are. This is an overview. As I said, and as it's written in some kind of classical story, classical in the sense it's not quantum. I just wrote down action functional, so then one needs to try to, say, quantize it. And if you do some perturbative quantization, so now let's call this was, let's say, classical. If you just try to do perturbative quantization of this guy, so if you, whatever, just symbolically write this path integral, so it's a function of f over all f's. Then one thing that happens that if you want to make sense of that, we need to introduce some cutoff, and the thing then depends on the cutoff, and what one needs to do is some kind of renormalization, so we need to also imagine that the G and H depend on the cutoff, and it will give us, in some limit, if the cutoff goes to 0, it will give us a renormalization group flow. Whatever those words mean, you should know, but okay, I pretend I know. So we're going to get RG renormalization group flow for G and H. So these things now depend on a scale. There are some differential equations that they satisfy. And which is simply, let me just suppress for the moment this H. Let's imagine that H is 0 or something. So then it is simply the Ricci flow. So T is the logarithm of the scale, and the metric depends on this scale. And there is whatever constant, which is not important, just is negative, and times the Ricci tensor of G. So there is a thing like that coming from perturbative quantization of that stuff. And we should expect something similar or more general happening here. Right? So this is a more general story where the Courant algebroid is. It doesn't have to be exact. So here we're going to have a generalized. Ricci flow. I didn't tell you what a Courant algebroid is. It will happen later, but it is some vector bundle, and the generalized metric is a sub-bundle of that vector bundle, and it is this V plus which is going to move. So this E is fixed, but V plus, as it sits inside of E, is going to move with the scale. So this guy is going to flow. Okay, before I move a little bit on, why should one be actually interested on this right-hand side? It's some kind of silly generalization. Why to do it? There is this part called T-duality in the title, and so one reason why to look at this side is that if you want to understand better what's happening here, it's good to sometimes to go to this more extended world. In particular, if you want to understand what is called T-duality, or it's useful to look at these generalized models. I will also get more to what I mean by T-duality later. And now this Ricci flow, or this generalized Ricci flow story, which will now tell us that T-duality, or I mean what is called really Poisson-Lie T-duality, some kind of more general T-duality, is actually compatible with the renormalization group flow. So somehow it is okay also on quantum level, at least to one loop or something. Okay, so, and the final story is, or is it, let me add here maybe one more thing. This was for the renormalization group flow. Then there is,
If you can shift everything up.
stay. Yeah.
Apparently we have this micro, so if someone forgets and asks, maybe you can repeat the question. Otherwise
Okay.
It's just on the left side, you write this flow equation for G, but not for H, but there's also one for H, or?
Yes, I said and didn't write it that I suppose that H is equal to 0. There is some kind of slightly more complicated version of the same thing where H also flows.
And it's all encoded more or less on the right-hand side, I'm assuming.
Yeah,
Okay.
that's where we're basically going, we're going to do, to say what is the right-hand side and how to see it naturally.
Thank you.
So there's a thing which is very related to the renormalization group flow. It is whether we're getting a conformal field theory here. So whether we're getting two-dimensional conformal field theory. So it's like conformality condition, or like I can call it like a string background equation, or string equations. So that's a story which contains also dilaton field, so I will not talk about it now, a bit later. But there is something now again happening here in some way, purely in some differential geometry, which is called generalized Laplace operator. So I will get there only tomorrow, but we're going to see what is a definition of what is generalized Ricci flow. Then there is some more elaborate version of the same thing, which I will explain what it means. And then maybe this part is at the same time like for this quantization and for something one can call superstring. One can then talk about the super part of the story. So there are all kinds of those horrors that I do understand, like say Ramon fields or gauge fields. So this would be for type 2. So this would be for type 1 or heterotic. And all of these, at least to some extent, they do have a counterpart here. So they do have some generalization that is here. So there would be some of the spinors and generating Dirac operators and something. Okay, so I hope it sounds scary enough. So that was what I was intending for. But what I will actually do today, I will explain you what are Courant algebroids and what is generalized metric. I hope there is somebody somewhere who doesn't know those things, but as I told you, try to pretend that You never heard about it. Then tomorrow, I'll tell you more about these things that are written here. Not sure whether I get to the last one. Let's see about it. But it will be, as I said, in the framework somehow of elementary differential geometry. I will just define those things, and we'll see that they have nice properties and that they can be used for some kind of physics statements. And then for the third part, I will actually go more into understanding this physics part of this right-hand side. So I will tell you more precisely what these strange two-dimensional sigma models, and more those boundary field theories, what they look like, and we'll try to do at least some elementary perturbative calculation and see how at least this generalized Ricci flow, how it really comes from some Feynman diagrams. Okay, so what we're going to do today will be just what are Courant algebroids, what is a generalized metric, and a little bit about what is this Poisson-Lie T-duality. Okay, so what is a Courant algebroid? So is there, actually, it's now an honest question. So is there anybody here who doesn't know what is a Courant algebroid? Oh, great, so that's very good. So Courant algebroid is some generalization of a Lie algebra with an invariant inner product. And generalization in the sense that it's no longer a vector space, but it's going to be a vector bundle. So I'll write down the definition. It doesn't look very transparent on the first sight. So a Courant algebroid, what is it? So it's a vector bundle E over M with some structure. So first of all, there is a pairing just on the fibers. So it's a non-degenerate symmetric pairing. The second thing is a bracket, so this, which takes two sections and produces another section. So this is what is called a Courant bracket. And finally, a thing that we wouldn't have for a Lie algebra within a product. It is a row with a vector bundle map going from E to Tm, which is called the anchor. And okay, and such that, and there is some list of axioms that don't look so bad. So if you have three sections, so let's say A, B, C are sections of E, then A, B, C. It satisfies some sort of Jacobi identity. It is Jacobi identity was written there, but it's written in a way that taking bracket with A is it acts as a derivation for the bracket itself, that we can write it this way. Let me write as the second thing why we actually have to write it in a certain way. It's because now this bracket doesn't have to be skew symmetric. So if you take its symmetric part, it's equal to, we can compute it by taking the pairing of A with itself. There is some 1/2, okay, not important. Then we take D, that's still a one form. I want to make it to a section of E, so this is done with the transpose of rho. So here, see, the transpose of rho goes from T star of M into E star, but this we just identify with E using the pairing. It's a strange, this one is the odd axiom in some sense. Everything else is done very easy, or natural. The third thing is that if we act with rho A onto the pairing of B and C, then this is what you would expect, especially if you already know the definition. So what we get is A acting on B and plus the same thing with A acting on C. Okay, and that's it. One can say these are the only axioms. And there is a little exercise that these three imply somehow two more things. One thing is that if you take rho of Courant bracket, then we'll get just the Lie bracket of rho's. And 5, that we have this kind of derivation property also for multiplying by a function. So a fb, if f is any function, is the same as f times ab and plus rho a acting on f, and this multiplied by b. Okay. I imagine this is completely useless to write it down, but probably I had to do it anyway. Let us think a bit about what these 5 things actually say. So, with the exception of 2, this is the odd thing. With the exception of 2, all of them basically say that this is what I can write down, that taking bracket with A is a derivation of our structure. So what does it mean exactly? So what I can say more precisely is that there is a what it's uniquely defined by this thing. There is a vector field on E, which projects to vector field. No, let's call it Z of A. Which, okay. Project to rho of A, and whose flow, if you let it flow, then it's actually an automorphism of the Courant algebroid. So preserving everything that you see. So that's why, although 1, 3, 4, and 5 are very natural things, 2, it looks kind of strange, but it's sort of the only thing that make it work. It also suggests there should be a better definition, and indeed there is a better definition, but let me just stay with this classical one. And since the classical one that I should write down who it was. So this is this thing was defined by Liu, Weinstein, and Xu, I don't know, maybe 95 or 97, okay. Oh, it's some of the millennium, basically. Okay, so what are examples? So first of all, if M is a point, then a Courant algebroid is the same as a Lie algebra with an invariant inner product of arbitrary signature with an invariant pairing. Then a Courant algebroid over a point is the same thing as a Lie algebra with an invariant pairing. So that's not very surprising. So this is one example. The second example is what is called the standard Courant algebroid. So now we take arbitrary manifold, and for E, let's take the tangent bundle. Then we want to have there some pairing, so for good measure, we add the cotangent bundle. Oops. So that we can have pairing between vectors and covectors. And now on this guy, we need to somehow invent the pairing, the bracket, and the anchor map. So what do we do? So if we take, let me start with the anchor map. So rho of some vector field and of some one form is the natural thing just to project onto the vector field. It's defined to be X. Now the pairing is that if we take a vector field and a one form, then this is alpha of X. But if we take two vector fields or two one forms, we get 0. So alpha beta is 0 is xy. This doesn't yet specify completely the structure, but if we then say that we take the Courant bracket of two vector fields, what can it be? It should, by this property 4, it should be just the Lie bracket of those vector fields, but maybe some one form. But if you say declare that this one form is 0, so if it, for this Courant bracket, if you just declare that it's equal to x, y, the ordinary Lie bracket, then from that, the rest of the story is easy to compute. So we'll get things like that x alpha is the Lie derivative of alpha, etc. So everything else can be then computed. And this is some kind of natural Courant algebroid. And it has also natural generalization or some kind of sheafified version, which is called an exact Courant algebroid. So what are exact Courant algebroid? So definition, a Courant algebroid E over M is exact if, so what do we have? We have that anchor map, which goes to Tm, and we also already used it once. There is this its transpose that goes from T star M, and let us add zeros here. So it's exact if this sequence is exact. So the standard Courant algebroid is exact. It's when this extension is just trivial. It's really Tm plus T star m. And then there is some kind of little observation, or which one can call theorem. So how to construct such a things? So or I can write it down. They are classified by the third cohomology of M with Euler coefficients. And more precisely, what is happening? So if you choose a splitting, an isotropic of our extension of star, it means that we have E, which goes to Tm, but now we somehow choose a splitting which goes to E, and isotropic, it's isotropic with respect to the pairing. So it's isotropic with respect to that, meaning that if you take two vectors and move them to here, their pairing is going to be 0. So what do we get then? So by choosing the pairing, the splitting, we now have that E is Tm plus T star m. And because we chose that splitting to be isotropic, we will have these same equations for the pairing. So the pairing is S for the standard but then there is a little bit of some choice somewhere. Okay, thanks a lot. Yeah. Maybe this side is. Okay, so then if one thinks a bit about what kind of equations we might get. So if you take this Courant bracket of x and y, then, okay, we don't know it. It might be something, but for sure we can say that the vector part is just the ordinary Lie bracket. That's this property 5 or something. No, it's property 4. But plus, there might be now a one form. This we don't know, but we chose it in an arbitrary way. And it's a little calculation or trying to, little of understanding to see what this one form looks like. So it turns out there is actually a 3 form where we plug in x, y, and leave the last slot empty, and that 3 form is closed. And yeah, I don't know, anyway, almost everybody, of course, knows this stuff, but some people don't. And if you like those silly exercises, then you can try to prove it. It's kind of to prove that this one form needs to be of this form. And then if you change the splitting, oh, by the way, how much time do I actually have? So is it, it's 1 hour, okay. So what happens if you change the splitting? You see, you have somehow T star, then we will have T, so this is our E. And if you take a new one, it still needs to be isotropic. So, and if you see it as a, so we will see this as the graph of a map, let me call it B, which goes from a linear map, which goes from T to T star. Then, because it's this thing is isotropic, then this B is actually skew symmetric. B is skew, in other words, it's a two form. Okay, and if you change the splitting, so what happens with H? That's again a small calculation that H is then replaced by H plus dB. So what, indeed, in this way, first of all, we did prove that when it comes to classification, so when we somehow now try to understand the regardless of the splitting, then the thing is classified by the third Drown cohomology. So that's one thing. And another thing that we may observe that when do we get like precisely the same thing? It's when B is closed. So we also get the automorphisms or say, let's say, the base preserving automorphisms, things that don't move M of an exact Courant algebroid is the same as the group of closed two forms. And then maybe it's kind of equivalent way of how to see those exact Courant algebroids that any.
Maybe you should write base preserving, because
okay.
before we had this
okay. Base. Mm-hmm. Yeah. Base preserving automorphisms is that's this group with the group operation is plus. And so an equivalent picture basically is that as we have our M, then locally our exact Courant algebroid, when we restrict to some reasonably small open subset, then it's going to be standard because, well, if you choose it, say, to be a ball so that the third cohomology vanishes, then it is isomorphic to the standard Courant algebroid. But then on the overlap, we're going to glue those two standard Courant algebroids using a closed two form. So that's another point of view how to understand those exact Courant algebroids. Okay. And now a non-trivial example. Yeah, I think I'll manage it, so it should be okay. Thank you. Oh, or maybe I don't. It's not so easy, right? So let us take what is called a Manning pair. So it's just we take a Lie algebra with a non-degenerate invariant pairing, and then inside of G, we take some H, which is a Lagrangian Lie subalgebra. So Lagrangian means that if we take the orthogonal with respect to that pairing to H, then it's equal to H. Lagrangian subalgebra. Now, let's imagine then that we find the corresponding groups and suppose that H is a closed subgroup or whatever, so I think things are all okay. Then if we take for M, G mod H, and for E, we take the trivial vector bundle G times G mod H. So this guy, this one is an exact Courant algebroid. Is an exact Courant algebroid in a natural way. So what is this natural way? So if you take constant sections, then say the bracket and also the pairing is just the Lie bracket and the pairing that we have on G. So I can just write that pairing and bracket is inherited from G. So this part is sort of stupid. But then there is the anchor map, which contains a little bit more of information. So the anchor map, which really is just given by, it's enough to say how it acts on constant things. So it's a map going from.
How do you define that?
Okay, so the question is, how do I define this pairing and the Courant bracket for non-constant sections?
No. How do you define what is constant?
Constant it's a trivial vector bundle.
Yeah.
So constant means just an element of G. That's what I meant. And then for non-constant, one just computes it using the XMLs. And okay, this row, which should go from G to whatever, to vector fields, roughly speaking, the M. So as you can guess, this is the action. The action of G on G mod H. This is an example which actually plays role in Poisson's T-duality, whatever that thing actually means. Okay.
So where do you need these conditions that Lagrangian subalgebra?
If you want to prove that it's exact, then you need to know that it's Lagrangian. If you want to prove that it's a Courant algebroid, that it actually works at all, then it's enough to know that it's a coisotropic Lie subalgebra. But somewhere in the calculation, this will show up. Yeah, it's a nice exercise. Yeah, try to prove that you actually do get an exact Courant algebra and try to see on the way where those things, which things are somehow used. Okay. Very good. So I should, that was maybe enough in general about Courant algebroids. Now, what is a generalized metric? Metric in a Courant algebroid E. So by definition, it is simply whatever I can write it this way: an orthogonal splitting of our vector bundle to two vector subbundles. One is called V plus and the other one V minus. And the only condition the condition is very mild. It doesn't use almost any of the structure. The only condition is that we want the pairing to be positive definite here and negative definite there. So such that this on B plus is positive definite and on V minus is negative. Definite. And then some small whatever, it's example / proposition, which says that if you have a generalized metric in an exact Courant algebroid, so rather said to say a pair. So if you have E, which is an exact Courant algebroid, and so instead of the splitting, I could just use V plus because V minus is the orthogonal complement. And the generalized metric inside of that. So this thing is equivalent to G, which is a Riemannian metric, and H, which is a closed three-form, both on M. Okay, now how does it work? So some kind of proof. So we have our exact Courant algebroid, so which contains T star, and we can choose a splitting. So this one is not natural, this T, we somehow choose it somehow. And then we have here this V plus. And by looking at the signature, we can say that dimension of rank of V plus is the same as the dimensions of the manifolds. That is the rank of T, which is the rank of T star. We can also say that V plus doesn't or intersects T star trivially because the pairing is positive definite here, whereas it's just 0 here. So there cannot be any non-trivial intersection. So then we can see V plus as the graph of something, of a linear map going from T to T star. And now the thing is that it will enable us to fix this splitting. So there is a unique way how to split it. So there is a unique splitting. Such that V plus is the graph of a symmetric linear map going from T to T star. This is what we call G. This is. So why is it? Because you see, if we take a different splitting, then we're adding something which is skew-symmetric. There's this B thing that was appearing there. So we can always scale the skew-symmetric part in a unique way. Okay, then one easily checks that this guy is actually positive definite. It comes from this V plus being positive definite. So finally, what we see that this data will give us a Riemann metric, but also some preferred splitting, and a splitting in a Courant algebroid is the same as a closed free form. So the splitting that induces H. Okay, so this was all for generalized metrics. There is not much, but okay, as you can imagine, what can one say about just a vector subbundle that satisfies almost nothing? So finally, let me get just a little bit to what is Poisson's T-duality. So it should probably deserve some kind of longer introduction, but it is also not so terribly important for the rest of whatever these lectures. So let me tell you first the case of no spectators, whatever that word means, those spectators. So what is it? So we'll be using these exact Courant algebroids, the ones that we see here. So how do we do it? We imagine that we have a Manning pair, H in G, and out of that we can now cook up our exact Courant algebroid, which is G times G mod H with the base G mod H. But if you also pick a generalized metric here, which is simply a vector subspace, which is maximally positive definite. So let's pick here also V plus. So it will give us a vector subbundle here, the same constant thingy sitting here. So inside of that, we're going to have V plus and times the base, G mod H. This is a generalized metric. So we have an exact Courant algebroid, a generalized metric there. So in other words, it is equivalent to a metric and a closed tree form. And I'm proud to remember, this closed tree form is also closed H, and it's not the same H as this one. So this is equivalent to whatever G and H underlined, which is now a closed tree form on G mod H. No duality whatsoever so far, but what happened at least, that out of this kind of finite data, in some sense it's all about some vector space, we obtained this vector bundle picture, which is then equivalent to this data, which is data needed to define a two-dimensional sigma model. So it gives us a 2D sigma model with the target G modulo H. And what we can do now, that we can choose a different H. So a different, let's call it H prime in G. What will give us? It will give us now, finally, we do all the same stuff. So finally, it will give us some kind of G prime and H prime on G mod H prime. So all of a sudden, we have a different two-dimensional sigma model. It's a different target. So that's why it's different. Yeah, tell me. Yes, sorry. So the question is whether the generalized metric is the same. Yeah, I'm using precisely the same construction, only the only thing that that go to replace this H, so we're going to get in primes everywhere. But it's the same generalized metric. That's important. So everything is somehow, this part is fixed. Only this part is different. And what is the statement, or one of possible ways how to state Poisson T-duality, is that these two sigma models are almost equivalent. Well, almost means now, might mean several things. One way how to say that they are equivalent as Hamiltonian systems up to finitely many degrees of freedom. So modulo some smaller reduction, they are equivalent. They have infinitely many degrees of freedom. These are strings moving somewhere. So now the statement is Poisson T-duality now says that these two sigma models are isomorphic Hamiltonian systems up to some finite stuff, which I will not write down right now. There is this story then has some generalization where in place of G, we start with some more involved Courant algebroid. I will mention this generalization tomorrow because today I should probably end in like 1 minute. So yeah, you can probably now ask questions.
Okay, other questions?
Sorry, that's a naive question. Are the string background equations invariant under this Poisson-Lie T-duality?
That's for tomorrow.
Okay.
Yeah, the answer is yes, but or modulo some minor stuff, but the answer is yes.
Can you get different signature metrics from this?
Okay, then this, wherever I wrote it, I forgot. Yeah, this thing. This positive definite and negative definite one, then one needs to have like other signatures. Then one needs to somehow worry a little bit about whether this is still true. And in general, it will not be true, so then we need to somehow either kick out those points where this property fails or do something.
Other further questions?
Can you say something about these finite dimensional degrees of freedom and what kind of control you have there?
Thank you. I was hoping somebody would ask me. I hope I will not take half an hour to explain. But still, I will erase one part of the blackboard. So what is the phase space, first of all? It's a Hamiltonian system, so what is the phase space, where it's happening? The target space is G mod H. So the phase space, is the loops in G mod H, and then T star of that. just the simplicity form is there, then twisted by this closed tree form there, but there's some story about it. But this is roughly speaking the phase space. But there is an equivalent way how to see it, which uses the data which is written there. We look at flat connections on an annulus. So this will be like flat G connections on this stuff. And they're modular space, but I should say like, what kind of modular space and what kind of flat connection. So there is a boundary condition on this inner thing, which says that those flat connections, they should actually, when we go to this inner circle, they should restrict to something which is in H. So it should be a one form with values in H. And also gauge transformations are also restricted to be in H, but only on this inner boundary. So say gauge transformations, oh, no, I shouldn't. So what is where? So here it's in H, inside it is in G, and finally on the outside there is no restriction for those connections, but the gauge transformations are restricted to be trivial. That's why this modular space is now infinite dimensional, because like we take arbitrary one forms with values in G, but modulo nothing. So, okay, so that's one way how to write down the phase space. And when you look at where does this H, I mean the Lie algebra H, where does this enter? It only enters here. So if you take some kind of reduced phase space, it's the same picture, but now with no hole. It has the same Hamiltonian. The Hamiltonian is some expression that I can write down, but it might be not so important, which uses V+. It uses this generalized metric, and it only cares about what's happening on the external circle. And so the reduction, there is this reduction. So what does it say? It says that we're taking only those connections whose holonomy along this inner circle is trivial, or we can just say, we can take holonomy then along any circle which is inside, so we take the trivial holonomy connections. So if you impose this constraint, then the thing is no longer symplectic, so then we need to somehow mod out by something, but in the end we end up exactly with a modular space of flat connections on a disk.
Can you repeat the reduction?
Yeah, so this, what is written here, this is the modular space of flat connections on a disk, on full disk, where the gauge transformations are restricted to be one on the external circle.
But how do you get the reduction? What is the tropic submanifold?
Yeah, so to go from here to there, we take only those classes of flat connections, this modular space of flat connections, whose holonomy, when you go around, is trivial. So that's the quasi-tropic submanifold. And it has finite codimension. Well, there is just the constraint is that the holonomy, which is an arbitrary element of H, needs to be 1. So the number of constraints is the dimension of H. Okay, and you see, now if you choose a different H, we're getting the same picture that after we do this reduction, we're getting that stuff. And now this is getting into this part of those exotic two-dimensional sigma models that one should understand this as something when there is no hole inside. So there is no longer any Manin pair, it's only G entering the game. So there is no longer any exact Courant algebroid behind, and there is the only Courant algebroid is G, the Lie algebra itself. Okay. And the right description is somehow, well, this is some kind of Hamiltonian description. The right description is in terms of Chern-Simon's theory, as you would probably.
Between these two, h, prime, you said there's a finite number of degrees of freedom.
Yeah, this is the difference. That here, these are two different moduli spaces, just two different phase spaces. If I take a different h, I'll get a different phase space. Maybe, should I write the Hamiltonian? So the Hamiltonian is a function of this one form of the connection. And it's something like 1/2 times integral over the outer circle. So this S1, or that's the S1. And if our connection there looks like whatever A sigma, D sigma, so sigma is the angle. Right? So this is sigma as we go around. Then what is it? It looks something that we need to take the plus part of A plus. It is the part that has values in V plus, and then minus the part which has values in V minus. So this difference is now positive definite, right? So this is positive definite, but that pairing is negative definite, so this minus will correct it to make it positive definite, and times d sigma. So these are functions of sigma. Right? So the Hamiltonian depends only on the form, on the boundary. So it's perfectly compatible with these reductions, which are somehow modify things only inside. This should look mysterious, like where it's coming from. Why should one do such a thing? So there will be a way better explanation on Thursday.